So on Wednesday, we spent a little bit of time on the boring administration stuff. Then we talked a fair amount about different aspects of what this course sort of is about. Scrolling all over the place like a drunken sailor. Sorry, I'm making you dizzy. And, you know, some of the differences between thermo and kinetics. Today, I want to spend just a little bit of time on microstructure and then hop over to a review of thermodynamics. So I'm going to start with looking at the iron-carbon phase diagram, because this is something that most people are familiar with, right? It's pretty complicated, but not too bad, right? Most of the time, as far as MSE folks go, we're really only concerned with this region here near the eutectoid point, right? Most of the common steels that we use are sort of in this hypoeutectoid region. Of course, the welders among us are very concerned about the paratectic region, right? Because they're coming from liquid most of the time. As metallurgists, I'm not particularly concerned about what's going on up here, right? This is all erased by the time I get here. But for the sake of it, I want everyone to consider a thought experiment, right? So we're going to consider a hypoeutectoid steel, meaning that we're to the left of this eutectoid point. We're going to then cool down. We're going to hold it at 1000 C, right? So up here, right? So from our phase diagram example, right? Our previous knowledge of phase diagrams, we see we're completely in the austenite phase field here. And I'm going to slowly cool to room temperature, right? So as we do that, I need a volunteer, glutton for punishment, to walk me through what's going to happen as I slowly cool down from this austenite phase field.
What composition are you at right now?
0.6% weight percent.
0.6, eh?
Yeah.
Well, all right, I'll give it a shot.
Okay, so who is this speaking?
This is Kevin Nutzling.
Cool beans. Okay, take it away, Kevin.
Well, as you slowly cool, the structure is going to become a lot more, I don't know what the word is, defined, for one thing. It's going to change from a solid austenite solution into a mixture of austenite and, well, not austenite, alpha and, was it gamma phase? What's the symbol?
Yeah, so the gamma phase is the austenite, right? And then what's this little window over here, the alpha phase?
Yeah, that's the,
right, so that's, no, that's ferrite.
Ferrite, sorry.
Right, so we enter into the austenite ferrite region here.
Mm-hmm. So ferrite will begin to develop within the microstructure, which will basically change from a homogeneous solid austenite structure to a austenite ferrite structure,
okay,
which will cause a number of dislocations, likely, if not outright, like interstitials or vacancies. I don't know the exact.
Okay,
well,
so yeah, we're not going to necessarily get any defects that form when we do this, when we have this growth, right? But but just keep walking down through the phase field, right? So when we're close, yeah.
All right. So now you have a mixture of austenite and ferrite, and then as you continue to cool from there, you'll get into the mixture of perlite and ferrite. The austenite is being transformed, correct?
Right.
And if you keep going from there, keep going?
Yeah, keep going down.
Going down, down, down. I don't remember if it's depends on how rapid you do it, but eventually once you get some Martenssite in there.
Yeah, so if we cool slowly at this composition, we shouldn't get any Martenssite.
All right, so if it keeps going slowly, it will just continue at this point until it becomes a stable, I believe, hypoeutectoid. Is that what it says?
It's hypoeutectoid, yeah. So we will have.
It's not going to shift structure anymore. I think it's just going to kind of stabilize and solidify, I believe.
Okay, so you got most of the main points, right? So as we cool down, right, we're going to hit this, what we call the A3 line, right, in which case we'll start nucleating ferrite in the austenite, right? It'll nucleate and grow, and we'll talk in detail about the mechanisms of how nucleation and growth happens, right? And eventually we'll come down here. So just when we're right above the A1 line at 723, we'll have a mixture of austenite and ferrite. When we cool down, we'll start to transform all of our austenite will go away. We'll nucleate and grow perlite, which is a mixture of cementite and ferrite, right? And eventually, if we cool it down slowly to room temperature, right? Notice how small this field is over here. If this were an equilibrium phase diagram, it would basically say we'd have a mixture of ferrite and graphite, but since it's the metastable phase diagram, it's going to predict that we have a mixture of ferrite and cementite. Okay, so what does the final structure look like, right? We have mostly perlite here, right? We can see the original austenite grain structure still, but we've transformed to essentially a composite between a metal and a ceramic, right? The cementite is a carbide ceramic, and the ferrite is a BCC metal. Okay, so let's do the same thing. We're going to do the same thing. We're going to hold rapidly. We're going to hold at 1,000 C for a long time, and then rapidly quench as fast as we can. Right? So our cooling rates are going to be hundreds of degrees per second, right? So that we get down to room temperature in 1 or 2 seconds.
In that case, my old materials, you described it as the material just kind of doesn't really know what to do. It doesn't properly develop, I believe, the ferrite it needs. And instead, it just starts sort of blue shift straight to Martenssite as the grains thicken and become a mess.
Exactly, right? So we get Martenssite, right? And this is the Martenssite structure that we would expect from a steel of about this composition, right? Notice how different, fundamentally different it looks, right? There is no equilibrium phase present here. There is no cementite carbide. Well, there are, but they're hidden, right? But for the most part, we see these long lenticular grains. What's the crystal structure of this Martenssite? Right? It's body-centered tetragonal, right? So it's not anything you're generally familiar with, right? It's not, BCC, FCC, HCP metals, right? It's got what's the carbon content of this Martenssite phase?
I believe it would be in the, well, if you're asking like for the microstructure, I believe it would be in the center, correct?
Well, no, I'm saying where's the carbon located, but if I were to take a small little region of this Martenssite and then do chemical analysis on it, what's the carbon content here?
The dark phase.
Right? Yeah, it's 0.6, right?
Mm-hmm.
Right? So it's a diffusionless transformation. Compare that to our perlite. If I took a small region in one of these ferrite ribs, what's the carbon content? Right? Yeah, it's
Shout
gonna,
out. Jump on us. That company. Shout out to Two Chefs. What's up? Oh, from Mississippi. Florida. Great.
so
Three beefs.
whoever's not
Site.
needed,
This one for the vacant 185 MMA belt that somebody ran away and left open. Don't do that running.
okay,
We got unknown.
get back to people so I can mute people. They need like a mute all button. Mute all, there it is. Okay. So, okay, so here the perlite is going to be whatever this composition is out here, 0.01% or so, right? Because we've diffused carbon away into the cementite structure. Let me pull the chat back up so I can keep an eye on that. Okay, so now here's the question. On this phase diagram, where's Martenssite? Right?
It's not on there.
It's not on there. It's metastable. Right? So here's the rub. Almost all engineering structures that we use, whether we're talking about metals or ceramics or polymers, most of the time we're reliant on metastable properties, metastable phases for the properties and performance of interest. Right? We need to find ways of locking in metastable structures, like say this Martenssite, and then modifying them so that we get the properties we want, right? What's the problem with just quenching this steel and leaving it as it is? Right? This Martenssite is incredibly strong. Right? Body-centered tetragonal, right? Not a lot of nice close packed planes. We don't get easy dislocation slip. Right? It's really brittle. There's no toughness here. Right? That's why we have to temper it. What are we doing when we temper Martenssite? Right? We want to diffuse the carbon out and transform regions of this to ferrite. Right? So we gain some of that toughness back. Right? So another example, right, where structure is super important, right? So here we have phase separation in polymers, right? So this started out life as a homogeneous mixture of two different polymers, right? And then you let it sit for a little over an hour, and now we've got these two separate, clearly separate regions. What's going on here? Someone throw out some ideas. Why does it separate into these weird shapes? Why not just little spheres?
The individual elements are attracted to themselves.
So not so much elements, right? These are long polymer chains, right? But what sort of physical parameters of this system can we think about, right? So if all of these interfaces have a surface energy associated with them, correct? Right? There's if there's an energy cost, right, to make a new region, right? So that means how could we minimize the surface energy of this? right? If we had all the polymers, if it was exactly split in half, right? If this block was half dark and half light, right? Then we have a nice, smooth, straight interface right down the middle. And there'd be a lot less surface area than if we had these long, tortuous shapes. Why doesn't that happen? What would require this to completely separate into two really nice, neat chunks? Right? It's more thermodynamically stable. Actually, we still haven't gotten to the thermodynamic, we haven't got to the stable minima yet, right? So there's long-range diffusion that needs to happen, right? I need to move all of this polymer down to here, this blob, right? What's the only mechanism for that to happen, right? Diffusion of one polymer through another. Do you think it's particularly easy for polymer chains to diffuse through each other? Not really, right? So the answer is this structure comes up because we only are dealing with essentially short-range diffusion, right? So if here's this chart is probably a little bit confusing, but we've got a miscibility gap here, and we can reduce our global free energy by making by diffusing down to these concentrations, X1 and X2, right, to go to the minimum of these wells. But that requires long-range diffusion in a huge amount of time. But as we'll see later on in the course when we talk about spinodal decomposition, it's really easy to separate to these inflection points on this curve, right, called the spinodal points, right? And that is what gives us the structure we have. It's a balance between the energy gained by the free energy change by separating the two phases versus the energy penalty associated with the interface. So in thermo, did you guys talk about the energetics of the interface, right? And how that's going to affect things? Generally not, right? Because it doesn't interfaces don't fall neatly, and defects don't fall neatly into the concept of chemical potential and activity and the nice thermodynamic concepts that we talk about, right? That's not to say those concepts aren't extremely important, but there's a lot more going on that drives the evolution of a material system than just the thermodynamics, right? It has to do with time, temperature, ease of activation, or ease of nucleation, ease of growth, right? And so we need to understand what are the driving force for these proper processes, and then what are the energetics and the kinetics associated with them, right? Okay, so let's hop on to some thermo, right? And this should be a review, right? But there might be things and concepts that you haven't quite thought about in maybe the same way before. Okay, so as a graduate student, I was lucky enough to have a thermo class from Michel Barsoum at Drexel University. And he is the guy who wrote that, I don't have it here, that orange textbook on ceramics that I showed up last time. And he has a quote that's not his originally. It's from some unknown person, but it will forever be linked to him in my mind. And he says, some people use thermodynamics as a drunk uses a lamppost, not so much for illumination as support, right? Thermo is viewed as a really abstract and confusing subject. Was someone saying something? Okay. So, but in reality, most of the principles are pretty simple, right? Where people get tripped up on is by focusing on the math instead of on the insight, right? And that's a natural thing when you're learning this subject, right? Because it's presented in terms of equations. And as a younger student, internalizing the meaning of differential equations is not necessarily the easiest thing to do, right? So I want to sort of strip away some of the equations and talk about some fundamental principles that I think are super important. Okay, so first off, let's move towards a concept of free energy. Okay, so a really common misconception, and even from people who've gone through thermodynamic training, right, is this thought that equilibrium is where the energy content or the enthalpy of a system is at a minimum. Okay? If that were true, many of the things around us would completely defy explanation, right? Any endothermic processes wouldn't be able to happen, right? So if we think about melting ice cubes in a bowl of water, right? The energy content or the enthalpy content of the liquid is higher than the solid, right? So that if we just think about equilibrium in terms of energy and enthalpy, that would not be sufficient to explain where the equilibrium is, right? And this is you hear it over and over again, even in people that should know better, especially when people are being careless in their language. Even people who do know better say things incorrectly. Okay, so Gibbs, right? He was really the first person to appreciate that there's another function that has to be minimized before equilibrium is reached, right? And I'm sure everyone had Professor Akbar, right, who's been teaching thermo for a long time, right? Everyone knows Gibbs free energy, right? And the first thing when anyone asks you anything about what's happening in a material system, your first answer should be Gibbs free energy, right? And we have to remember Gibbs is Gibbs pointed out that, right, it's the enthalpy plus a term from the entropy times the temperature, right? So the equilibrium depends on the temperature explicitly, not on an implicit contribution through the heat content and the enthalpy, right? And that was sort of the common way of thinking before Gibbs, right? But the importance of entropy here really can't be understated, right? And it's weird when you think about it, right? Because entropy, in a macroscopic sense, has temperature in the denominator, right? And heat in the numerator. So it would seem that the temperature would just cancel out, and it would make more sense to write this as enthalpy minus change in heat, which is a lot more difficult to interpret, but doesn't, right? I don't know. Sometimes I think about things in unusual ways. But let's keep going. So let's start with this enthalpy term and the first law, and then we'll get back to this entropy term here. Oh, shoot. I just realized something. Okay, so there's a couple examples in here that we're going to have to look at on Monday because I forgot to set up the iPad to write that out. So I have no way of drawing on the screen unless with the mouse, which means no one will be able to read. So there's a couple worked examples through the notes, and I'm going to skip back to those on Monday. Okay, so heat, right? So this might be a dumb question, but what's heat?
Heat is thermal energy, energy that can be felt as actually doesn't really need to.
Heat's a confusing one, right? So it is totally a measure of kinetic energy, right? It's the vibrations, right? So when we talk about heat flow, it's confusing because heat is not a substance, right? So it's something that can do work on a substance or material, but it's not a substance that flows in and of itself. Mathematically, we treat it that way, right? But it's definitely not. We talk about heat flow and heat transfer in the same way that we talk about mass transfer. But it's definitely not, right? So we have many ways to change the temperature of a substance, right? We can transfer mechanical, electrical, chemical, or radiant energy, right? We can do work on the substance, right? So the first law is all about this balance between heat and work, right? So a system that performs a certain amount of work on its surroundings is going to, and receives an amount of heat, is going to change its internal energy, right? So the change in internal energy is just this balance between heat and work, okay? So internal energy is a state property. It's a state variable. So it's independent of the path of how we do it, right? It doesn't matter for the change in internal energy how we do the work and how we absorb the heat, right? But Q and W are. Oops, this should say are not state functions. Everyone right now, put not right here. Shoot. My ability to make stupid mistakes is infinite. Hopefully I'll catch most of them. But anyway, this should be not, right? So the heat, so Q and W depend on the path they take, right? And so that's how we indicate it in the mathematics. Little d means exact differential, capital D means not, right? So state variables get a little d, non-state variables get a big D, right? Okay, so let's suppose we have a system, right? And it extends a force through some path, right? The work done by the system is going to be essentially given by the force times our path differential, right? And so if we consider this piston doing work on the surrounding, right? So this fluid here is expanding, right? Exerting pressure on this, force on this piston, which is then moving it, and it's doing work on the surroundings here, right? If this occurs slowly enough and there's no friction, right, this is going to be reversible, and our work, our differential in work is just going to be PDV, right? Pressure volume work, everyone's familiar with this. And provided these changes are reversible, we can then write our first law as our change in internal energy is our change in heat minus PDV, right? Hopefully nothing surprising here. Okay, so here's just an example that I wanted to do, right? We'll get back to this real fast. Okay, so motivation for the enthalpy, right? We know that, right? So in the first law, we talked about heat. We didn't talk about this concept of enthalpy. Why do we need the concept of enthalpy? So when we absorb a small quantity of heat, its temperature is going to rise by some amount dt, right? Small change in heat, small change in temperature, right? The ratio of these two is the heat capacity, right? But we said before that dq is not a state function, right? So therefore, it seems odd, this heat capacity is a function of the path, right? And that causes us bookkeeping problems. It's not easy to work with this, right? But we can simplify everything by introducing an enthalpy function, right? That's our internal energy plus PV, right? These are all state functions, right? The instantaneous pressure, the instantaneous volume, and the internal energy, which we said before was a state function. Okay, great. So now we've got a state variable that's comprised of other state variables, but how on earth does this actually help? Well, imagine we have a constant pressure process, right? So our first law, as stated before, right, if we just take the differential of H, right, we now have dq minus dw plus pdv plus vdp. If it's constant pressure and dw is pdv, and obviously vdp disappears, right, what we get is that our differential in enthalpy is our differential in heat at constant pressure. Right?
Professor, somebody's got a question in the chat.
Oh, okay.
They would like to know why the Q in the heat capacity ratio has a little d.
Probably because I screwed up. Yep. Yep, I was inconsistent with my notation. I'll fix these couple typos and get back. But yeah, good catch. Right. I even specifically say dq here is not a state function. Right, but right, and this should be a capital H. Okay, so the physical meaning of the enthalpy is the heat absorbed or released during a constant pressure process, right? Which is something that I think a lot of people sort of don't quite appreciate the utility of, right? Most of the time for materials, are we in a constant pressure state or a constant volume state? What are most of the processes that we're thinking about? Right, most of the time we're thinking about a hunk of something under atmospheric pressure, right? So enthalpy is our variable of interest here, right? Right, simply because we're most of the time under a constant pressure regime, right? So this heat that's absorbed or lost during that process is the change in enthalpy of our material, right? We can also define a constant pressure specific heat, right? Which is our ratio of enthalpy to temperature at constant pressure, right? And we can integrate that, our specific heat, constant pressure specific heat, to find the energy change in our enthalpy change in our material as we go up, as we change our temperature, okay? But we have no absolute energy scale, right? Everything in thermodynamics, we're generally talking about relative changes with the exception of temperature, right? There, we do have an absolute temperature scale, but we have no absolute energy scale. So we have to define an arbitrary standard energy state to relate all of these other changes to, right? What is our standard state? Well, we say that the enthalpy of formation of all elements at 298 Kelvin is what we're going to define to be zero energy, right? So this is just an arbitrary thing, but it's the standard that we all sort of agree on. Okay, so then I wanted to use this for another example where we look at calculating the enthalpy. Montaigne. Oh, I hate autocorrect. You know how many times I look at these notes before I post them? And I never can find any typos or errors. And then I put them up and immediately a whole bunch just jump out. So keep me honest, right? Anytime you see something wrong, let me know and then I can fix it. Right, but we want to calculate the enthalpy changes of alumina and aluminum at various temperatures, just to sort of work through this example. Okay. What about if we have a constant volume process? Well, if the volume of the system is maintained, we obviously have no work, right? Because we have no PDV term, right? So that means our change in internal energy is just our heat, right? So if we're at constant volume, Q becomes essentially becomes an exact differential. So little dq equals big dq for this particular case, okay? So the increase or decrease in internal energy under a constant volume process is the heat absorbed or rejected, okay? So what about elastic strain? What happens to a solid when you heat it up? Right? It tends to have thermal expansion, right? If we confine it to the same volume and we heat it up, what are we changing internally? Right? We now have, think about a thought experiment, right? The change in internal energy is path independent, right? It's a state variable, so it doesn't matter how we get there. So let's do an experiment where we heat it up under constant pressure. The volume is going to change. Our hunk of stuff is going to get bigger. And then if we want to make it constant volume again, we can apply a really high pressure and squish it back down to its original shape. So the internal energy hasn't changed. Now let's pretend we do that compression isothermally. So we heat the object up, we bring in heat. That raises our internal energy, right? Right? We have an enthalpy increase during our constant pressure process. Then we increase the pressure and squish it back down for a constant volume process, right? Now our internal energy is going to increase because of the energy of the elastic strain put into all of those bonds, right? All of the atomic bonds are now at a different length than they want to be, right? They're reacting against the force that's confining them all down, right? And that's essentially the thought experiment of where enthalpy comes from, right? We can think about thermal expansion and then compression back down, right? And that the fact that the internal energy is equal to the heat absorbed for this constant volume process means that the energy that we're absorbing doesn't just go into raising the temperature, it also has to go into deformation, changing the bonding energy of our solid, right? So all of these things are sort of intricately tied together, in perhaps confusing ways, right? So if we go back and look at our enthalpy, right, we essentially see that that's what the correction built back into here is. That's why there's this PV term here. Is you can think about this as a thermal expansion correction under constant volume versus constant pressure processes, right? That's one way of looking at it. A different way of looking at it than you'll see in most textbooks. Okay, so quick review of just the main points from the first law, right? And I'm sure that was probably the entire first exam from 2251, right? Is that about correct? I don't know exactly the pacing for Professor Akbar, right? And we covered that in about 15 minutes, right? So there's a huge amount of details in there that you guys have seen before that I'm completely glossing over. I just want to bring some ideas back into your minds, right? So let's think about the second law, right? And there's a fantastic book that's long out of print that's just called Entropy, right? And it's by this guy by the name of J.D. Fast, who was the chief scientist at Philips when they were a light bulb company back in the 1960s. But in here, he has a wonderful thought analogy that I thought to motivate the concept of entropy. And when I first read this as a student a long time ago, it resonated with me and it really stuck, right? So imagine that you've got a car on the top of a mountain, right? And we roll the car down the mountain, right? It's going down. Obviously, you don't have to use the accelerator, right? You're going to be riding on those brakes pretty hard, though, going down a steep incline, right? What's happening as you're braking, right? You've got brake pads rubbing against the rotor, a huge amount of friction, and you're transforming that kinetic energy, right? The potential energy wants to turn into kinetic energy and make your car go faster and faster down the hill. On the other hand, I've got brake pads that are squeezing the brake rotors and turning that kinetic energy into friction, right? Which is being dissipated as heat through my brake rotors. And if it's a really long hill, those suckers are going to get red hot, right? So all of this is fine with the first law, right? I've got a really nice energy balance here. I can calculate how much heat, how much potential energy I've lost, how much kinetic energy I should have gained, and how much energy I dissipated as heat. And it all wraps up in a nice, tidy sum, right? First law is happy. Now, if that balance was all that mattered, I should be able to take an acetylene torch, heat my brake rotors back up to red hot, and my car should magically go back up the hill, right? If it was a reversible process, if all that mattered was the energy balance, right? We know that that doesn't happen, right? That's an absurd thing to say is going to happen, right? I heat up my car and it's going to float. It's going to go back up the mountain, right? But from a purely energetic point of view, there's nothing to stop that, right? We live with the concept of entropy, right? Even before you took thermo, you were at least familiar with it, right? That this crazy idea that the universe tends towards disorder and that there's a direction to things, right? You may not have had it in the same type of vocabulary, but I mean, it's around us, right? It's in everyday language. But think back to the 1800s, right? And trying to ask the question, when I do work, I get heat. Why can't I turn heat into work? And that's a really profound concept. At least to me it is. I think that's a really profound concept. And I've spent a lot of time over the years thinking about entropy. And every time I think I understand it, I get confused again in my head. Right? And when I say I get confused in my head, I don't mean like I forget how to do the equations. But there's always some little bit, something new that I think about that says, oh, there's a subtlety here I didn't quite grasp before, right? And I've been thinking about this on a near daily basis for 20 years, right? So there's a lot of room for growth in your sophistication of thought, even on concepts that you think you understand really, really well, right? So definitional, right? We know that entropy is the thermodynamic quantity that represents the unavailability of the system's thermal energy to be converted into mechanical work, right? It's interpreted as the degree of disorder or randomness in the system. It's easy to transform work into heat. If only we could do the reverse, we could all be miracle workers. But we unfortunately can't, because we have to contend with the concept of entropy, right? So, dumb question. Oh, so what is a steam engine, right? Well, so you are extracting, converting heat into work there, but there's a limit to how much work you can get out of a steam engine. There's a thermodynamic limit that you can't exceed.
It's also extremely inefficient. We can convert work into heat with almost 100% efficiency. We can convert work with about 40% efficiency at best.
Yeah, we've got the essentially, Carnot was the first one to figure that out, and Carnot did that before the concept of entropy was actually really formalized, right? So, huge number of smart people. There's a saying that says the steam engine taught us more about thermodynamics than thermodynamics taught us about the steam engine. And I think that's true, right? Our ability to build something often comes before our ability to understand how it works.
So basically, we built this thing for out, hey, if we heat this up and move these pistons and causes this train to go, and then only later the people start again, wait, why does this happen?
Why does this happen? How do we build a better steam engine? Right? Okay, so we know we have the macroscopic definition of entropy. ds is dq by dt. There has to be a reversible here, right? This is a heat applied in a reversible manner. We have the microscopic definition that Boltzmann is famous for, S equals K ln omega, right? Where omega is the total number of possible configurations of the system. We're going to talk about what this omega means in just a little bit, right? But the condition here is, what is the possible configurations at constant energy, right? Okay, so you may or may not have seen this before, right? This is Boltzmann's grave, right, with his famous equation engraved into it. But what I really want to point out is that Boltzmann was a hipster, right? You can walk down any city and see 100 guys that look like him, right? I wish I had this sick haircut and my beard was half as majestic, right? I bet you Boltzmann would look great in skinny jeans and a tight shirt, right? And I think that is where we're going to stop for today. So coming up next week on Monday, I want to work through the examples that we have and finish going through this part of the critical thermodynamics review. If we're lucky, we might get to discussing Gibbs free energy and phase diagrams, which I hope. If not, we'll pick that back up on Wednesday. So have a great weekend, everybody. Oh, 2 quick things. So on Monday morning, the reading quiz will be available, right? It should only take you like a minute or so to go through it, but it will be open starting at 8 o'clock, right? So you'll have, there's plenty of time. Also on the Martenssite, there is a poll for the TA office hours, right? So if there are times where you have bad classes, where you cannot meet for office hours because of scheduling conflicts and things like that, please make sure that you fill out the poll or the survey so that we can find times for office hours that work for the great majority of everybody. Okay? Have a good weekend. And we'll see you all on Monday.